Have you ever been fascinated by the behavior of jelly at different temperatures? Well, what exactly gives rise to these properties? In this video, we'll be exploring the change in chemical and physical structure of jelly to explain this phenomenon. Jelly is commonly made at home using commercially sold powders which contain gelatin. Let's first examine the structure of collagen. The basic structure of a collagen fiber is made up of aggregates of collagen fibrils. Collagen used to make gelatin in jellies is largely derived from animals. Collagen fibrils comprise of tropocollagen molecules, which are linked together by covalent crosslinks. These covalent crosslinks exist between the carboxyl end of one tropocollagen molecule and the amino end of another. Tropocollagen comprises of 3 alpha helix chains super twisted around each other. The tropocollagen molecule is held together by extensive hydrogen bonds as well as covalent crosslinks, thus leading to the high tensile strength of the molecule. Alpha chains form the secondary structure of the collagen molecule, each with a left-handed helical conformation. The primary structure of collagen comprises of amino acids, usually in the form glycine XY, where X and Y are amino acids such as hydroxyproline and proline. This shows part of the structure of a gelatin molecule. Glycine exists every 3 residues. Being the smallest amino acid, it is the only one that can fit into the center of the triple helix in the tertiary structure. In the making of jelly, the gelatin is heated to 40 degrees. The gelatin now exists as random coils of polypeptide chains, mostly in its primary structure. As the solution is put into a mold and left to cool, partial renaturation occurs in 2 steps. The first step is known as the collagen fold, where the coils of gelatin partially regain the collagen structure. In denatured form, most of the peptide bonds exist in the cis conformation, whereas in more complex structures, it exists in the trans conformation. Thus, in order for the secondary structure to reform, peptide bonds in gelatin have to undergo cis-trans isomerization. This is the slow rate-determining step of the renaturation process. The next step is intermolecular crosslinking, involving hydrophobic hydrogen and ionic bonds. These bonds can be disrupted on heating, and hence the gel is thermoreversible. When the jelly is heated, it will cease to be a gel and regain its liquid state.
Gelatin powder can be easily purchased from any markets or supermarkets. The gelatin powder is added to a bowl of water, which was preheated to 45 to 50 degrees Celsius. This is the step whereby denaturation occurs. The solution is stirred to ensure homogeneity. Thereafter, the solution is cooled in the fridge to allow for renaturation. After the solution is cooled, it becomes edible jelly. To prove the process of denaturation and renaturation, we reheated the jelly to show that it will liquefy. A few blocks of jelly were placed in the pot and subjected to mild heating. After 3 to 5 minutes, the gelatin regains its liquid state. The solution can then be cooled down again to its solid state. This shows that gelatin is thermoreversible due to its structure and the nature of bonds. However, the gelatin doesn't gel under certain conditions, such as the addition of pineapples or any protease containing fruits. Pineapples contain a chemical called bromelain, which contains 2 proteases. Bromelain prevents gelling due to its ability to separate amino acids by breaking down the peptide bonds as soon as they are formed. Now that we have learned the chemistry behind jelly, eating jelly can never be the same again.
Yeah.